3:30 in Kansas and whatever time is in your place. Vasily Krylov will give his second lecture about Higgs and Coulomb branches, geometry, and representation theory. Please.
Yes, again, thank you very much for the invitation. So, first of all, maybe let me just briefly recall what we had last time, at least parts. And as always, please ask questions. So last time we discussed that whenever we have some quiver Q and the additional data of these dimension vectors V and framing vectors W, we can associate to this triple the gauge group that I denoted by G and representation of this group N, finite dimensional representation, and to G and N, one can finally associate what I called BFN Coulomb branch. That's some non-commutative algebra quantizing some Poisson variety, and it depends on lambda and mu in my notations. And remember that the information of lambda and mu is basically the same as the information of V and W, just packaged in a different way, such that lambda and mu are now weights of the Lie algebra corresponding to the quiver Q. So we have this interesting associative algebra that I denote like this. And let me also remind you that we discussed that when our quiver Q is special, namely is of type ADE, Dynkin quiver, then this algebra is closely related to so-called shifted Yangian that is defined by some relations. We have some E, F, and H generators. When the shift mu is 0, this Yangian is isomorphic to the ordinary, like Greenfield Yangian, corresponding to GQ. And the relation between the shifted Yangian and our Coulomb branch is the following. So the Coulomb branch is always isomorphic to a certain quotient of this, certain very concrete quotient of this Yangian called truncated shifted Yangian. And lambda corresponds to truncation here. Truncation. And these are parameters, they correspond to flavor parameters in the Coulomb branch. So they correspond to the fact that Coulomb branch is actually a family of algebras. Finally, we discussed that this map is compatible with like these integrable systems, with commutative subalgebras that we have inside of the Yangian, a subalgebra generated by H, and inside the Coulomb branch, we have a natural commutative subalgebra coming from the equivariant cohomology of a point. Okay, so any questions about this? So that's sort of what we discussed last time. Okay, great. Then let me now tell you a couple words about the representation theory of the shifted Yangians, like what people study. So whenever we have the shifted Yangian, y mu, then there is some natural category of representations one can associate to it, and it's so-called category O of y mu, defined by Hernandez and collaborators. So this is some analog of the ordinary BGG category O in this infinite dimensional setting. And roughly speaking, object in this category O is a module that I denote by M over this shifted Yangian. And this module should be finitely generated, and it should satisfy properties very similar to ordinary BGG category O properties. Namely, the operators EI, K, should act on this module locally nilpotently. So in some sense, again, this module grows down. So we have some generators and then it grows down. And the second, also very natural from BGG category O condition, is that the Cartan TQ generated by these loop generators, and let me emphasize here that we're only considering these like lower level of loop generators. In principle, we have higher things. We have IA, I2, and so on. But for the category O, we require these like just ordinary Cartan to act locally finitely on our module. So generalized eigenspaces should be finite dimensional, and our module should be the direct sum of these generalized eigenspaces.
Well, I have a question because there will be a lot of representation theory today, I believe. Not every slice is a symplectic resolution of singularity, but let's pretend that it is. Then that Webster with several collaborators long ago defined a very general framework for the categories of O. All right, so what's the relationship of that very general stuff where you do not need precisely the BFN realization
Absolutely.
yeah.
That's precisely this case. So if you restrict yourself to these Coulomb branches, and again, know that Coulomb branch, you can talk about it for arbitrary quiver Q, not necessarily for the AD quiver. And like all of the conjecture that I will formulate today make sense for arbitrary quiver. So yes, precisely if you apply this general setting by Webster and collaborators, and being more careful, Webster and collaborators, they only considered the case when our, so this in BLPW2, they only consider the case when our X, that is like in our situation is a Coulomb branch, is conical. But these Coulomb branches, they very often are not conical, and that's very important to include them into this story. So in this generality, this was done, like the category O and basics of it were worked out carefully by a student of Joel Kamnitzer, Alexis Leroy-Lapierre. Indeed,
What's his name again?
Alexis Leroy-Lapierre. I'm not sure that
Leroy.
I will write it correctly.
Yeah, but there is a paper in archive, yeah,
Yeah,
probably.
he has a paper on archive called asymptotic characters and something.
Mm-hmm.
So in particular, he discusses this category O story in general, and these categories O I'm talking about for the Yangian. Remember that Coulomb branches are quotients of the Yangian. So the categories, so this will be compatible with categories O. So
yeah, because if I remember correctly, in that old story, this BLPW, well, 2, indeed, uh, mm, mm, uh, they need two actions of C star on the symplectic manifold, and so this conical structure gives one of them. So, and for the definition of the category, you indeed need two actions of C star. And you say that this guy Alexis, he defined the category O without this extra.
you do need an additional, but this is some interesting feature of Coulomb branches that I didn't discuss, but note that on a Coulomb branch you always have. So actually, you see, we have this torus TQ here. It actually integrates to a torus T that acts on the Coulomb branch. And that's a very general feature of Coulomb branches. We always have a quiver Coulomb branches. We always have a torus large enough that acts on them Hamiltonially. And moreover, it's large enough in the following sense. The fixed points of the Coulomb branch under the action of this torus, it's always either one point or empty. And when it's empty, there will be no category O. It will be just like empty. And if it's a point, then there will be an interesting category O that has finite number of objects. Finite, as in BLP, number of objects. And this property that it has finite number of objects precisely corresponds to the fact that this torus acts as with only one
Sorry, finite number of simple objects because
simple objects. Sorry. Yes, absolutely. Thank you. Of simple objects. So it's category, it's like a finite category.
Okay, so this fact about fixed points, it replaces the conical structure, yeah, because in that case, okay.
You can put it this way. Yes.
Yeah. All right.
Yes. Yeah, thank you very much. Yes, that's indeed a very important question. So, yeah, summarizing, one can say that indeed Coulomb branches is a very nice framework for these categories of. Okay, so yeah, but like people who study Yangians, they don't like think about Coulomb branches, they just deal with Yangians. But maybe the point of my talk, one of the points of my talk will be that sometimes it's useful to use Coulomb branches to understand something about purely algebraic things like modules over Yangians. So, and yeah, here is one reason why the Coulomb branches are useful from some algebraic perspective. That's due to Hernandez and Young theorem that they prove that whenever you have some object L that is an irreducible object in this category O for the Yangian, that I will denote by just O mu from now on, then actually there are always parameters R and this lambda such that the action of the Yangian on this L factors through the Coulomb branch action. So in other words, Coulomb branches see all irreducible modules over the Yangians.
Well, it's shifted Yangians, yeah?
Shifted Yangians.
And they were not defined independently on this Coulomb branch business.
They are. They are. Yes. So you see, like this shifted Yangian, it's literally just this. This literally just the same definition as the Drinfield's original definition.
Yeah, but just historically, were they discovered independently on?
I think, yeah, they were originally discovered by Brandon and Kleshov, who studied finite W algebras in type
Okay.
A.
Yeah.
Yes, but then indeed they were like studied by Kamnitzer and collaborators in the context of quantizations of slices and affine Grassmannians, and then people realized that these slices and affine Grassmannians are particular cases of Coulomb branches. Yes.
All right.
Okay, so now let me very briefly say like how people study modules over shifted Yangians or over Coulomb branches, over algebras in general. So whenever we have a module M over shifted Yangian or over Coulomb branch, then the most standard thing that we can do is to ask about the character of this module, namely like to control the size of this module. And what is a character? Remember that we have this torus, the algebra of a torus, T, that acts on M. So we can literally just take a character with respect to this torus action. Namely, we sum over all weights that appear, take dimension, and sum z to the power eta, where z is a formal parameter. Remember that these spaces are finite dimensional. So that's one thing that one can do. And there is one much more refined invariant that I will call graded trace of a module. And how it works. So remember that we have a large commutative subalgebra that I denote by H. We both in Coulomb branch, in the Yangian. And then whenever we have an element of this commutative subalgebra, then we can compute the graded trace of this element acting on our module. Namely, again, we have a grading by weight spaces for this small torus T, And then we can take the trace of x acting on the corresponding weight component, the same weighted sum by z to the power eta. And in this way, we get a functional from our large commutative subalgebra to formal functions in z to the power eta. And if we substitute x equal to 1, then we will recover the ordinary character as before. And another name for this graded trace is Q character. That goes back to Frenkel and Reshetikhin. So that's just another, in the case of shifted Yangians, that's just another way to package the information of the Q character. Any questions about the definition of this graded trace?
So Frenkel and Reshetikhin, you mean their work on quantum affine algebra at the beginning of 90s?
Absolutely, yeah. Yes. But the idea is the same.
Okay.
You call this Q characters, and somehow the Q will be coming from a one-dimensional torus action. And here the torus T is for the Lie algebra. So how can I see the Q?
So frankly speaking, I don't know why they call it Q character.
Oh, I see. Okay.
Yes.
maybe because they think that x is equal q in the power some Cartan element.
Maybe.
In the power rho.
I see. Okay.
Maybe.
Yeah, when the z equals q.
Yeah. So since it's a linguistic so deviation, there are also QQ characters of Nikita Nekrasov. So this type of characters, do they appear in relation?
We will get to them. I think that we will get to them. For me, there will be some vertex functions of Okonyakov. Yes. We will. I think we will get to them.
Okay.
Okay, so, and yeah, maybe let me just make a couple remarks like why these graded traces are important in representation theory. One reason is that if you know the graded character, the graded trace of your module, then it determines the class of your module in K0 uniquely. In other words, this map is an embedding. And again, that was the reason why Frenkel and Reshetikhin originally introduced Q characters. And the second remark is that if our module over shifted Yangian was actually a module over the Coulomb branch, for example, it was simple, then if we want to compute this graded trace, then as we know, it's just a functional on this algebra. So we can completely forget about the shifted Yangian and just live in this Coulomb branch setting. Okay, any questions so far? So from now on, we will deal with Coulomb branches. We will forget about shifted Yangians. I will return to them and to some representation theory associated to them during the third lecture. But today, my goal would be to understand like how to think about these graded traces in general for Coulomb branches. So let me discuss the object that controls these graded traces. Again, remember that graded trace was a map like this. And one useful thing to do would be the following. Like by the very definition, it's just a function of this on this large commutative subalgebra. But what we can do, we can extend it to the zero weight component of our algebra A, where by A0, I mean, remember that we had this torus T, and it acts on our algebra A, and it gives a grading of A into the weight spaces, and we take degree 0 part. And then literally the same definition of a trace, it makes sense and gives us a functional from this space to this space. That is C of Z linear. Okay, like literally the same formula. Just take graded trace of an element. But after we formulated it this way, we can now use the trace property to conclude that actually our functional effectively factors for a certain much smaller quotient that is called D module of graded traces and was originally introduced by Kamnitzer, McBreen, and Proudfoot. So let me explain who is this object. Again, the claim is that this trace that we care about actually factors through something much smaller. And who is this Gerter of A? Again, that's something very natural, namely, we're asking the following question. We're taking trace of M of some element, and usually when we're taking ordinary trace, then trace of AB minus trace of BA is 0. But here the trace is graded, so we should remember about this grading. So then the following thing will be equal to 0, where A has degree minus eta and B has degree eta. So this is some type of, again, Hochschild homology of our algebra. And then, since we want to think about traces as about some formal functions in Z, we consider some completion of this space at 0. That I denote by Gerter of A. So this is the space on which traces live. And note that this space, one can show that this space is already finitely generated C of Z module. So our A0 of Z was huge, it was infinite dimensional, but after you take this quotient, you get something of a reasonable size.
I'm a bit confused with the term. You say that this space is called D module of graded traces.
This one, yes.
Why D module?
It has a D module structure of graded traces. Just to save time, I will not explain it carefully, like how, I mean, how the action looks like. But the D that acts is more or less differential operators on this torus T, again, some completed version, where we think about T like functions on T as about functions in these Z variables that we have here.
So I'm confused because, well, I'm totally lost. I thought that T is some Hamiltonian torus of whatever dimension it is, and Z is what? I thought that.
So you see that, for example, eta is an element of, it's a character. So it's like, so about Z to the power eta, you can think it about function on this torus T.
Okay, so Z is also not a single Z, it's not...
Yes, it's
okay.
like a formal symbol, and you see here eta, yes, it's like eta lives in like character lattice for the torus T, so it's like multivariable thing.
Yeah, okay, that's fine.
Okay, any other questions about that? Okay, so in the upshot here is the following. So the trace of a module in the category O over Coulomb range is an example of a functional on this D module that I denote like this. And more general functionals on these D modules are, so I will call them graded traces. So not arbitrary functional on this object comes as a trace of some module. It's more general concept. And how one should think about these graded traces. So another way to think about them is that this is some formal version of so-called twisted traces, T-twisted traces. So let me recall this object. T-twisted trace, it depends on an element T in our torus acting on our algebra. And it's a functional from our algebra to complex numbers that is that has t-twisted trace property in the following sense, that if you apply the functional to AB, then it will be equal to trace of BA, but A is twisted by this automorphism T for any A and B. And if you look at this definition, so what we're modding out by here, you see that this is just a formal version of this condition.
May I ask, it's maybe a stupid question, but still, either a twisted version of Hochschild and cyclic homology.
Yes, I think that the right way to think about this object from that perspective is that we are like maybe about this object. Yes, that about this object. Yes. So let me put it here. So alternatively, like ordinary traces, they correspond to functionals on the commutator of A, on the quotient of A by the commutator. That is the Hochschild homology of A. And now this t-twisted thing is the following. You can still consider A as a bimodule over itself, but the action on
one action is twisted.
Is twisted, exactly.
Yeah. But the question is, my question is that you see, well, it's Hochschild homology. It's not periodic cyclic, but still, sometimes the Gauss-Manin connection gives rise to a connection or whatever demodule structure on the Hochschild homology, not just on periodic cyclic. So is this demodule structure an instance of or a version of this?
That's probably true. Yes. As we will discuss this particular demodule, that's the reason why I don't want to like talk a lot about the demodule structure, especially and spend. So this particular as a demodule, it will not be so complicated. So it's interesting as a space classifying all of these traces. We will describe the demodule structure of it either.
Okay, all
by
right.
the end of the talk. And indeed, it will have some additional Q deformation that comes from so-called quantum demodule that is very interesting and non-trivial.
Okay, interesting. Okay, go ahead.
Okay, and let me maybe just mention that these twisted traces and these like formal versions, they naturally appear from the physics side, namely they are so-called, like Gayota and Okazaki explained that they should be referred as partition functions corresponding to this theory.
So they have two papers. It's the one about sphere with the word sphere.
I think so.
Yeah.
Yes.
Okay.
Yes. I think so. Yes. And another place where these twisted traces appeared naturally, they are closely connected to these so-called short star products, defined, I think, by Beam, Pillars, Rostelli, and then further studied by Etingoff and Stryker. And I even think that that was an idea of Kontsevich, that to classify, there is a relation between short star products and these T-twisted traces.
Yeah, that's exactly true. Pasha gave a talk at IHS and he mentioned that explicitly. Okay.
So yeah, these twisted trace and these things are just like formal versions of them. Okay, and my goal for today will be the following. I will explain some conjectural framework to study these graded traces on arbitrary Coulomb branches. And this will be a theorem for ADE quivers and for Jordan, for the quiver, which is one loop. And in general, that will be just some explicit conjectural description.
So, and for people who are foreign to, I don't know, even to Coulomb branches, but like representation theory, just you want to describe all whatever, I don't know, what kind of representations, all representations.
Essentially, yes. So as we just discussed, whenever you have a representation, you can associate to it its graded trace. This graded trace determines the class of representation in K0 of category O uniquely, and this framework will tell us that arbitrary graded trace, in particular the graded trace for representation, has some geometric description.
Okay.
Okay. So now I will change. So okay. So maybe let me. So what we're trying to do, we have this space of traces, and we have a map from this cartan of Z to this space, and one can show that this map is actually surjective, and it's a homomorphism of D modules that I'm not explaining a lot. And what we want to do, we want to understand this space as a quotient of this H of Z. Because remember, originally our graded trace was a functional on this thing. So the Q character is a functional on this guy. So we want to understand this space as a quotient of this larger thing H of Z. And it turns out that the 3D dual side helps here. But maybe any questions before I proceed with the 3D dual picture. So our goal is to understand the whole map. Okay, then how, so let me just recall some notations first. So remember, I denoted by MH tilde the Higgs branch of our theorem. And in this particular case, it's the Nakajima quiver variety corresponding to our quiver Q. That is defined as we take fiber over 0 of the moment map. We consider some open subset here consisting of stable points. And then we mod out by the action of the gauge group that I denote by GV. Remember that this is just the product of GLVI, and the action is free, so this quotient is smooth and symplectic. Smooth and symplectic. And it's absolutely crucial that by the very definition, it embeds as an open subset inside the same sticky quotient. So we're not imposing this stability condition, and the action is not, it's not free anymore, but we still can form a sticky quotient, and I will denote this sticky quotient by X, and we have an open embedding. And also remember that we had this flavor torus that acted on representation, and so it also acts on our quotient, and it also acts here. And we have this C star H bar that corresponds to the contracting action. So this is a Hamiltonian torus. This is the torus that scales the symplectic form on our space. Okay? Any questions about these notations? Okay, great. So now let me briefly explain who is this quasi-map quantum D module that one can associate to Nakajima quiver variety, and that goes back to Okounykov's school and to a particular paper by Pushkar, Smirnov, Tseitlin. They are not studying quantum D module there, they study quantum cohomology, but one can do quantum D module story similarly. So the idea is the following. Remember that we have this X that is a sticky quotient, and we also have our quiver variety that is MH tilde. And there is a natural correspondence between these two spaces consisting of maps from the fixed curve P1 to the sticky quotient such that infinity goes to our quiver variety. Remember that quiver variety is open inside the sticky quotient, and sometimes people call it quasi-maps to quiver variety, because generically they go to MH tilde, but for example, 0 usually goes to this sticky quotient. And we also, these maps have some degree that we fix. And we have an additional C star action. I will denote it by C star Q. So this action, it is the action on the curve P1. And we have two maps, evaluation at 0, evaluation at infinity. And here I should be careful. Namely, this map, evaluation at infinity, it's not proper if we just define it this way. So actually, one should compactify this modular space slightly at infinity, and then this map becomes proper. And I put hat here, following Akunkov, emphasizing that this is now a proper map. That goes to the quiverate. And then whenever we have such a correspondence, we obtain a diagram, like pull-push diagram, from the equivariant cohomology of our sticky quotient. And here we also have these z parameters, and these are literally the same z's as we had before, but they are on the dual side. So previously, you remember the z had to do with the torus acting. Now it has to do with the degree of our curve. So this d will live in some effective cone, as always. And we will land into equivariant cohomology of our MH tilde. And this map here that Akunkov calls capped vertex function is given by this correspondence, namely we sum over all of the degrees, pull back for evaluation at 0, then you multiply by some virtual structure shift, and then you push forward under this proper map evaluation head. And you sum over all d with weights z to the power d. And the claim is that in this way, and so any questions about this? Okay, and the claim is that in this way, one gets a map from this space, and you see this H is the same H that we had before. Now on the Higgs side, these are Z, and we also have this additional Q, which comes from you see we have an additional data of a curve P1 on which C star Q acts. We didn't have it like on the Coulomb branch side, this Q. Now we have this additional Q, and we have a map from this space to this space that I will call Q. And the claim is that this space should be referred as a quantum version of this Kirwan map. So it's a homomorphism of D modules, and this Q is a quantum D module that I would also call a quantum quasi-map D module.
So I would be maybe happy. So the thing is that first I do not quite understand what's the D module structure of this H of Z. Second, I do not understand why even if you have a proper map, you don't have a complex of D modules and have a single D module. This pull back, push forward construction.
Yes. What do you mean by complex of D modules?
I mean, if you take pull back, well, if you have a push forward, I mean, this is a operation on the derived category, not on the abelian category of D modules. mean,
At
at
the
least
moment, we're
technically.
doing everything in cohomology.
Yeah, but you said something about D modules. For cohomology, I am fine. But you said that it's this pullback push for this correspondence, whatever, the last visible, clearly visible line, that it have homomorphism of D modules. I do not understand this phrase.
So it's like, there is maybe more familiar D module that one can associate whenever we have variety like MH tilde, then if you consider, in this case, you should consider equivariant, say C star H bar equivariant and MH tilde Z, so then this thing, there is this, I should refer to Dubrovin, right? Dubrovin's quantum
Yeah, good.
D module. So that's the same type of thing, but defined differently.
Yeah, but then you use correspondence and you kind of pull back it, then push forward, and anything can happen to a single D module on the way to final destination. So you still get just a single D
Yes.
module.
The claim is that this map is a surjective map.
Yeah.
That you can even treat this Q, the definition of this quantum D module is the following. You consider here just the classical D module, so something that does not depend on Z at all and just corresponds to like the standard action of H2 of this X on this thing. And then the claim is that the kernel of this map is an ideal for the D module structure. So
Okay.
yeah, so it's like you should treat this as a quantum Kirwan map that starts with something classical and makes it quantum.
Yeah. Okay.
And the most interesting part is the map itself, this V hat.
Yeah. All right. Go ahead.
Okay. Any other questions about this object? So this is something that people who like Akunkov and go around are studying. That's a very interesting and complicated structure. Solutions are certain hypergeometric functions, and so on and so on. So I have one simple example that I can explain, but maybe later. So, okay, so now let me return to our story. So in our story, this object that we are trying to understand, it's also a D module, but solutions, as we just discussed, of this D module, some of them are traces of representations. And one can show, that, for example, that follows from this paper by Ettinghoff and Stryker, that trace of a module will always be a rational function in Z. Like trace of Verma module, it's like at 1. It's like 1 divided by some product. So it's always rational. Nothing hypergeometric here. So the D module that we are considering, it's much simpler than this quantum D module. And this is good. So now let me formulate the conjecture. And the first version of this conjecture is due to Kamnitzer, McBreen, and Proudfoot. And they also assume that mu is dominant. We will get rid of this assumption. And they conjecture that this D module we were trying to understand, these graded traces of A, is isomorphic to a certain very particular so-called Calabi-Yau specialization of this Giventhal's or Gromov-Wheaton's D module. So you remember we have this H bar parameter, we have this additional Q parameter that comes from the action on P1, and they conjecture that these two D modules must be isomorphic. And that's what they call quantum Hikita conjecture. But note that in this conjecture, there is no H of Z, And obviously, like if we want to apply this to something, to study of graded traces, then we want to understand them as functionals on this h of z. So we should be able to see this h of z on the right-hand side. And also, there is no explicit description of this thing. So it's some specialization of this Gromov-Witten D module, but it's still not explicit. So now so the claim is that if one replaces this Gromov-Witten D module by this quasi-map D module specialized to h bar equal to q, then both of the issues here will be resolved. Let me explain this, but yeah, before, are there any questions?
So this Kamnitzer and with collaborators, if I remember correctly, they consider symplectic resolutions as a framework.
Yes, McBreen and Proudfoot.
Yeah.
Indeed. The point is that, again, what is really nice about these quiver theories and Coulomb branches. So, like on the representation theoretic side, we have this Coulomb branch AC quantized by some algebra, and indeed, this MC has no resolution in general, and it's not conical. But on the Higgs side, we always have an Nakajima covariety, which is non-singular. So this D module this quasi-map D module is always well-defined. You always have a resolution on one side, precisely on the side where you care.
Okay.
Yes, and maybe yeah, indeed, they considered the setting. They didn't consider Higgs and Coulomb branch setting, but they considered the general setting. But I believe that these conjectures should be considered precisely in this Higgs and Coulomb branch setting. For example, we have some like counterexamples to some limits of these conjectures when we are dealing with theories that don't come from quiver gauge theories. So it's important here that we are starting with a quiver and then associating to it Higgs and Coulomb branch. For example, it has to do with the fact that the Kirwan type map might not be surjective in general. So this McGerty-Nevins result about surjectivity, it's special for quiver varieties.
Yeah, I asked because I remember that the D module on the other side, they considered sort of a dual conic but symplectic resolutions, and they throw away some hyperplanes, which you don't do.
I'm not doing it here because I'm doing, yes, so you see, we always complete at zero because from the perspective of representation theory,
Yeah.
when you compute characters, you always compute them as formal functions. But indeed, you're right. On both sides, these D modules are well defined as spaces on some completed version of our torus with some hyperplane being removed.
Yeah. Okay.
And the conjecture is that yes, these like global D modules are also isomorphic. Okay, so yeah, so now let me explain like why this D module resolves the problem. So remember that we had this quantum Kirwan map, and now we can specialize h bar equal to q in this story. So do this Calabi-Yau. Sorry, one moment. My pen. Just 1 second. Connecting pen. Okay, yeah. Yeah. So we can do this Calabi-Yau specialization. So we still have this quantum Kirwan map here. And now the claim is that, so previously, you remember that we were considering this correspondence, and I said that we should compactify it at infinity. But then it turns out that after this h bar equal to q limit, after this specialization, literally the correspondence just given by these quasi-maps, with evaluation at 0 being not a proper map, it does give you a well-defined map, well-defined without localization. And in this case, you get a map from h of z to just to a classical D module. By classical, I mean here that is just given by like dx plus the classical multiplication. So previously it was a quantum multiplication. Here is just a classical multiplication that does not depend on z. And then one can prove again that after this h bar equal to q specialization, this map called vertex function, not capped vertex, just vertex function, induces an isomorphism between this specialized thing and the classical Z module for the Higgs branch. So we do have this surjective map from H, and we do know how to describe our specialization. It's just this. So secretly nothing quantum happens, and the only quantum thing that appears is this map itself, defined using pull-back, push-forward diagram, but now without any compactifications. Any questions about that? So let me now formulate the main conjecture/theorem, and conjecture means that it should be true for arbitrary quiver Q, arbitrary, without any restrictions, and we can prove it for ADE, where lambda is the sum of minuscules and no conditions on mu needed. In particular, the Coulomb branch doesn't have to be conical, or in the Jordan quiver case, and that's due to Hunter, Dinkins, Karpov, and myself. We call it refined quantum Hikita conjecture. So it claims that there should be an isomorphism between these D modules that we started with, this space of graded traces, as a quotient of h of z. And on the right-hand side, we have just a classical D module. That's the reason why I told you that as a D module, this object is quite simple. There's like nothing quantum in it. And this map comes from this vertex function specialized to h bar equal to q. And what isn't?
No, I mean, what is conjecture and what is theorem?
So yeah, theorem conjecture is that this should be true. That this should be true for arbitrary quiver, for Q being ADE quiver, or Q being a Jordan quiver. This is the theorem. So like the most interesting objects for representation theory, like as we discussed. Again, conjecturally, for arbitrary quivers, there should also be some interesting shifted Yangians with interesting representation theory. People just like are not studying them so far. Any other questions?
So the theorem for you said for Jordan quiver is true, and
Yes.
another non-ADE very simple one is the chronicle quiver.
Yes. For the chronicle quiver, let me think for a second. So the same, I mean, next time I will explain, first of all, the idea of the proof, and secondly, maybe even more importantly, some applications and like relation to some concrete representation theory. So in principle, the approach that we propose should work for arbitrary, say type A affine quiver, but there are still some missing details.
And I assume that when you say arbitrary quiver, the quiver could have loops at the vertex because the Jordan quiver is of this type.
Yes, we do allow loops.
Okay.
Yeah, absolutely. Yes, loops are allowed. The thing is that like if you have loops, then this algebra behind it, like previously it was shifted Yangian, now it will be something that has to do with something like double head, right? So for example, for this like Jordan quiver, we will see this GL1 double head shifted things. So it's not literally a quantum group, it's something quantum toroidal. Any other questions? Okay, so now let me explain a corollary, finally. So what we wanted to understand. We wanted to understand the graded traces on our algebra A. And this theorem slash conjecture tells us that these graded traces are functionals, but now on the right-hand side. So previously, that by the very definition, they were functionals on the left-hand side. But now they are functionals on the right-hand side, on the cohomology of our quiver variety in Z, that we can definitely identify with Borel-Moore homology of the quiver variety. But now we can use the geometry of quiver variety to describe functionals on it. Namely, whenever you have a quiver variety, there is a perfect integration pairing between equivariant Borel-Moore homology of MH tilde and equivariant homology of L, where L is the following thing. Our quiver variety maps naturally to its like affine version, and then one can take a fiber over 0. This will be a proper but singular variety, and they pair perfectly, like this one and our quiver variety. Integration pairing is perfect with values in equivariant cohomology of a point. So this tells us that arbitrary functional on this space is just an integration pairing with some class here. So the upshot is that any graded trace as a functional on this h of z, as we wanted, from h of z here, is given by the following formula. You start with x, that is an element here, then you do this quasi-map correspondence, so you apply this, like you do this evaluation at 0, so you do this evaluation at 0, pullback of x, and so on. So you get some class on x, and then you pair it with a class on L. Something in homology of this space L. Any questions about that? So this gives you some dictionary of passing from one side to the other, whenever you know that the conjecture is true. Okay, and maybe the remaining minute, I will just make a comment that everything makes a perfect sense for K-theory. One should just replace cohomology by quiver varieties by K-theory. Like everywhere, you just replace cohomology by K-theory, and then the Coulomb branch will be replaced by the multiplicative version of this Coulomb branch. And again, like for AD quivers, we can prove this conjecture that it's true for generic Q, roughly when Q is not a root of unity. So in other, and as we know, like representation theory at roots of unity for quantum groups is much more different than the one for generic Q. Again, conjecture should be true even for roots of unity. And the final remark, just to relate this story with something like very classical that has nothing to do with traces representation theory, and that's actually how I started to think about this story. So if you look at this conjectural identification, and then you make some like drastic simplification in some sense. Namely, you just substitute all of these z parameters to be equal to 0. H bar is equal to 0, so it becomes classical. F flavor parameters are also, everything is 0. Then on the right hand side, you will just get an algebra. And this algebra is cohomology of the quiver variety. And then this conjecture tells you, in this case, that this algebra will be isomorphic as a finite dimensional graded algebra to functions on the schematic fixed points of the Coulomb branch with respect to the torus T. Remember, I told you that as a set, this fixed point is 1. So one, like only one fixed point as a set. But schematically, it's an interesting non-reduced structure. It has an interesting non-reduced structure. And this non-reduced structure precisely captures the algebra structure of the cohomology of the Coulomb branch, of the Higgs branch. That was the original Hikita conjecture. And actually, this goes back to De Concini and Precesi, like very classical result, where they realized that cohomology of flag varieties as an algebra can be identified with functions on the schematic intersection of the nilpotent cone for SLN with Cartan. So that's precisely the particular case of this story. This thing will be functions on the schematic fixed points for this torus T corresponding to the Cartan. Okay, so let me finish here.
Yeah, thank you. Are there any questions?
Very quick question on the last Pepchini Procesi. So the nilpotent part intersecting with H and geometrical points are just 0, but in terms of schemes. So the function algebra is always finite dimensional in this case assume, right?
Absolutely.
So that is the cohomology ring of the flag variety for
absolutely. Yes.
Okay, thank you.
Yeah, I have a question. Maybe it's to the very beginning when Yangians still were present. But in any case, you start with a quiver, whatever class is. Can you add the potential to the quiver?
That's actually a great question. So we are. Let me think for a second. Yes, so definitely there should be. So the short answer is I don't know, but I do believe that the answer is yes, there should be some variation of this story of 4 quivers with potential. And even more. So like I would say that there are lots of things that we are that we are not we haven't tried doing in this story. Yes, one thing adding a potential. So, but what should be the dual thing in this case? I don't know at the moment. The other thing is that, as you see, we always take zero Hochschild homology. My guess is that the right thing to do would be to take the whole Hochschild complex and treat it as a complex. So yeah, there are. Okay, answering your question, I don't know, but definitely there is something here. So maybe I should also advertise one result. So what we will discuss next time. So you see, like here we have some general conjecture, but then one can ask the following quite natural question. Okay, so we have like on the left hand side, we have a bunch of, like if D modules are isomorphic, then the solutions of these D modules should also be compatible in some way. And on the left hand side, whenever you have a category O, you have a natural collection of objects in this category O, namely so-called Verma modules. So you always have here a bunch of solutions labeled by Verma modules, and this they are actually labeled by like fixed points on resolutions of our Coulomb branches. And one might ask, like, how to see these solutions on the other side. The answer is that these solutions are precisely these vertex functions specialized to a like dual fixed point. So they, in other words, in terms of this dictionary that we had before, they correspond to simplest possible classes that one can take in homology of this L. Namely, you just take a class of a fixed point. You're not taking some complicated subvariety, you're just taking class of a fixed point. And then it turns out that this statement, it has a categorification, that is due to, they're still working on this, but Spencer Tamagni and Tomasa Rebota. So they claim that actually the categorical version of this statement is that our Coulomb branch actually acts on some critical cohomology of this moduli space of quasimaps from P1 that to MH tilde, sending infinity to this particular fixed point P check. And when they
AC is quantum, yeah, it's quantum.
Yes, that's our quantized Coulomb branch. Yes, quantized Coulomb branch. And when they define this object, they actually explain, and this is due to Spencer, that this space has an interpretation. It corresponds, like this critical cohomology is actually a cohomology of some space with some vanishing cycle shift, and this vanishing cycle shift comes from some potential. So you enlarge your quiver, you add some potential, and then you compute critical cohomology.
Yeah, you see, one of the motivations for my first question was that this, in this Yangian and shifted Yangian business, cohomological whole algebra is in fact the kind of the basic object you can take in its double in certain sense. You can produce shifted Yangians. So
absolutely, that's how they prove this theorem, I think.
Yeah, so that's what I mean. That probably
absolutely.
There is an action. Yeah, all right.
Absolutely, there is an action. But again, I don't know how to modify, like how to add critical to like the objects that we're dealing with, like these objects, like classifying these traces. But like, yeah.
Yeah, I don't. Yeah, indeed, there is a lot of stuff. I believe even today, I saw maybe yesterday I saw the paper by Alyosha Latintsev with some other people about the vertex algebra structure. They finally managed to add the potential to Joyce construction. So yeah, so then in the end, it should be either factorization algebra or I don't know, maybe some three-Calabi-Yau structure. Yeah, okay, good. And your paper with Dinkins and Karpov, does it exist?
It will appear like hopefully within a month. Yes, yes, it doesn't exist. Yes.
Yeah. Okay, good. All right. Well, thank you, and please email me again the updated slides. Yeah, very interesting, and looking forward for your last lecture tomorrow.
Sure. Thank you.
Bye.
Bye.